So once again, our job in this problem is to calculate the power associated with each element, to figure out the direction of that power flow, and then to use all of those power values to determine whether or not this circuit is satisfying conservation of energy. A few spoiler alerts. There's only one current or voltage source in the problem, so that one is definitely going to be the one that is delivering power or supplying power to the rest of the circuit. The resistors, passive elements, they have to be absorbing power. If we find that that's not the case, then we know that we've made a mistake. Also, does it verify, does it obey the conservation of energy? Yes, it does. I guarantee it. And so anytime that you're solving a problem like this, it should, at the end, balance. And if it doesn't, again, one of two things is true. Either you've made a little algebra mistake or conservation of energy is false. My money's on the algebra mistake. So let's go ahead and label a few things here. I'm going to have this being I1, and this will be V1. And then we're going to have I2. And this will be V2. Notice that I always draw them so that the positive terminal is going to get the arrow of the current. And then here is I4, and this will be V4. Okay, so what we need to do is we need to calculate those 8 voltages and currents, or if we use the shortcuts, we could get away with just calculating 4 of them. We will eventually need to know both the current and the voltage associated with this source right here. There's no shortcut for current sources or for voltage sources, but we're going to be able to make some good progress with the shortcuts we do have. I'm going to combine the two 8 ohm resistors here on the right hand side together, and I know that because they're equal in value, when I combine them together in parallel, it's going to be half as much. So I'm going to go ahead and redraw the circuit here. And I'm going to have one 8 ohm resistor right here. Some of these values are going to work out to be the same, and that can be a little bit confusing, but it's also kind of convenient because the math works out to be nice and even. So here's 8, oh, I'm sorry, not 8. This one is 4 because I just combined two 8 ohm resistors together. This is V3. Of course, it's also V4 because V3 equals V4. I'll just make a note of that down here. V3 equals V4. And I know that this is still V2 plus to minus. I2 is flowing through that 4 ohm resistor. This is V1 plus to minus, and this is I1 flowing down through that resistor. And then here we have 12 amps. So we now have a circumstance where we can combine the two 4 ohm resistors in series. And if we do that, we're still going to have I2 flowing through both of those. So let me just quickly draw one last version of this circuit diagram. So I'm going to have a resistor right here. This is going to be 8 ohms. And before I move on, let me just label this as V1, and this is I1. And I know that I2 is flowing out right here, and that is going to be going through the series combination. This is going to be I2 that's flowing down. 4 ohms plus 4 ohms is going to give me 8 ohms. And so I have two resistors that are each 8 ohms. And I have I2 flowing down there. Now, I can't really label that as V2 or V3 or V4. All of those 3 resistors have been combined together, so it's really not helpful anymore to label, or it's not possible to label it as any of those 3 values. But what I can do is I can use current division to say that I1 is going to be 12 amps times 8 ohms divided by 8 ohms plus 8 ohms, which is going to give me 6 amps. Or, as you could guess, if you have a current flowing into a parallel combination of 2 equal resistors, just by a symmetry argument, you'd know that half is going to go into each of them. So then I could also go ahead and solve it the full way, or I could get away probably with just the symmetry, but I'm going to go ahead and do it the full way. Don't want to encourage shortcuts unless they're valid shortcuts. So we got the 2 currents, I1 and I2. Now, I can go back up to the original circuit diagram and see that I2 is now flowing into this terminal right here. So I2 is right here, and I3 and I4 are going to be the 2 parallel resistors that are going to split that current. And you know what? I will go ahead and accept this as a shortcut here because those 2 8 ohm resistors are equal to each other. So therefore, I can say that I3 is equal to I4, which is equal to 6 amps divided by 2, which is 3 amps. So it's very interesting what's happening in this circuit. The 12 amp source is sending 12 amps into this branch, and then half of that 12 amps is going downward. So 6 amps is going down, and then other half is going to the right. And then that 6 amps gets further divided by 2 into I3 and I4. It's just kind of a little interesting aside. It's not part of what we were asked to find in this problem, but it is an interesting little observation. So I'm going to go ahead and label P1. I think we can all understand that P1 is the power associated with the 8 ohm resistor that is labeled with V1. So P1, well, I could calculate the voltage there, but I don't really need to. I can just calculate it using the shortcut equation as I1 squared times R. And that's going to end up being 6 squared times 8, which is 288 watts. And because the arrow is going into the positive terminal, I know that that's being absorbed. And it's positive, which means that it genuinely is being absorbed, and it should be because it's a resistor. P2 is going to be I2 squared times R, which it turns out is 6 squared times 4, which is 144 watts being absorbed. P3, that's going to be I3 squared times R, which is going to be 3 squared times 8, which is 72 watts being absorbed. And then similarly, P4 is going to be I4 squared times R, which is, again, 3 squared times 8. Which is, again, 72 watts absorbed. So we now found the power associated with each of the 4 resistors, but we still have to find the power associated with the current source. Now, the power associated with the current source, we're going to need to have a voltage. We've already got V1 labeled, so I'm going to go ahead and relabel V1 over here, plus to minus. A problem is that the current is flowing into the negative terminal, so I could say, well, this current, I'm going to label it as negative 12 amps, is flowing into the positive terminal. So I'll just go ahead and include that negative sign. You know what? We understand that it is going to definitely be power that's being supplied by this element. I want to show you the full math so that you'll see that it all does work out. Do we know the value of V1? Well, not yet, but we can calculate the value of V1. V1 is going to be, let me scroll back up here, is I1 times 8 ohms. Because I know that in this resistor right here, I1 is flowing downward, there are 8 ohms associated with that resistor, and V1 is the voltage that appears across it. Well, I1 is 6 amps, multiplied by 8 ohms is going to give us 48 volts. And so then I can say P associated with the 12 amp source is going to be negative 12 amps times 48 volts, which is negative 576 watts being absorbed, which is positive 576 watts being supplied, and either of those is an acceptable final answer. I'll go ahead and circle that one. Now we have 2 ways that we can approach the final answer to this question, and that is that we can add up the power that's being absorbed. And if you add 288 plus 144 plus 72 plus 72, that's equal to 576. Use your own calculator, verify it, because that's important that you understand that I'm not just pulling your leg here. So 576 watts being absorbed, 576 watts being supplied. It all works out, it balances, conservation of energy. Or what we could do is we could just say the total sum of the power absorbed by all the circuit elements has to add up to 0. We would say 288 plus 144 plus 72 plus 72 minus 576. Because remember, here this was minus 576 watts being absorbed. When we add all of that up, it does, in fact, equal 0. And so therefore, we see the conservation of energy has been satisfied.